Well, in my early schooling, which was tended to be technical and engineering and science, we didn't study very much history. And the only bit of the history that I remember or had any interest in was in the history 1760 to 1820, which was the period of the Industrial Revolution. And I learned about steam engines and Newcomen's first steam engine, and there was an applied in Stephenson's rocket, which was the first steam-propelled locomotive. So at the age of 13, it was very fascinating to be in the Science Museum here in Kensington and to see the actual rocket that Stephenson had put together. I grew up on the South Yorkshire coalfield in a small mining village, and I was a little unfortunate. I didn't make the cut for the 11+ examination, but fortunately at the age of 13 I was able to get a technical transfer to Mexborough Technical School, and there I became interested in technical subjects. I left there at the age of 16 and went to join the Parkgate Iron and Steel Company near Rotherham, which was the only employment opportunity rather than going down the coal mine. So it didn't take someone to be of great brilliance to be able to decide above ground or below ground. So having joined Parkgate Iron and Steel Company, it was very fortunate that they had a very expansive secondary educational program, and at any one time probably had 300 or 400 of their employees studying in night school. And so I set to work to study metallurgy, which was the mandatory subject for management trainees in Parkgate Iron and Steel Company. And I studied at Rotherham Technical School, and by the time I was 20 years old I had a higher national certificate and a licence at shipping metallurgy from the Institute of Metallurgists. Coming to the subject of the good luck of location, as I mentioned earlier, the Parkgate Iron and Steel Company was my first employer, and it turned out that they had a very strong relationship with the University of Sheffield, 10 or 12 miles away, and they had a system for sending one of their promising employees or promising students to the University of Sheffield to study full-time rather than part-time, as I've been studying before, 4 years of part-time at Rotherham Tech. So I was fortunate enough in 1960 to get the scholarship to go to Sheffield University, where I obtained the degree of AMet, Associateship in Metallurgy. This was a backdoor way into the university because you didn't need the normal university entrance credentials, 2 foreign languages including Latin and other things, and this was a vehicle for individuals to get from something not the most privileged educational system into the back door of the university. And it turned out that this back door was the vehicle or the path for several metallurgists who became very successful over time. These include Brian Pickering, Terry Gladman and Bob Keown, including myself. I finished the AMet examinations, and which were, I thought, relatively easy as a result of full-time study rather than part-time study, and I apparently received very good marks, and I was invited by the University of Sheffield to stay on and to do a master's degree and a PhD degree. And again, I don't want to overemphasize the power of good luck, but I was invited to study for a master's degree under the direction of Jack Woodhead, who by then had just finished the 1 year of supervision of Bill Morrison's work on low carbon Niobium steels. And I was able to follow up on Bill's ideas and eventually wrote my thesis which was based on carbide precipitation and yielding in mild steels containing niobium. I mentioned earlier the fortunate timing of my beginning interest in the science of low-carbon niobium steels. In Europe, this was a very fertile period for research on niobium strengthening mechanisms or microalloying strengthening mechanisms. There were very big research efforts in British Iron and Steel Research in Sheffield, University of Birmingham, CRM, Centre Research de Metallurgie in Belgium. We had the CSM in Rome, Brozzo and Celasco, IRSID, Le Bon and his co-workers, all researching very actively in the very early 60s. So there's a lot of research focused on these low-carbon steels at that time. The BISRA research gave rise to the term perlite reduced steels, PRS steels, which had from 0.03 to 0.06% carbon. This is in contrast to the active steels of the day. The Great Lakes first pipeline steel in 1959 had between 0.22 and 0.26% carbon. This lowering of the carbon is a foundation for the emergence of niobium microalloying, because it facilitates the dissolution of the maximum quantities of niobium at the reheating temperature. The BISRA research at the same time also gave rise to the discovery of the titanium nitride heat affected zone grain refinement with Terry George, who was an Australian. He went back to Australia and pioneered the application of low-carbon niobium microalloy titanium treated steels at BlueScope Steel. As far as the study of the fundamental mechanisms of strengthening in the low-carbon steels, it seemed like the Sheffield University group was slightly ahead of its peers at the time. And I attribute this to the wisdom of Jack Woodhead. Jack Woodhead, as Bill Morrison's supervisor, had introduced the idea of separating grain refining effects from precipitation hardening effects by means of Petch equations, and looking at the deviation from the Petch equation, any deviation from that had to be attributable to precipitation hardening effects. So Bill was able to elucidate or hypothesize about precipitation of niobium carbide in austenite and in ferrite. And he postulated that he couldn't see the precipitates in ferrite, he saw them in austenite, but he postulated that they must exist, but he was unable to see them with electron microscopy techniques at the time. In my work, we developed a sensitive carbon extraction replica technique using very light etching, and we were able to see the 20 or 30 angstrom particles, 2 or 3 nanometers in today's parlance, that were the origin of the precipitation hardening in ferrite. So again, using this sensitive replica technique, later on, a few years later, I was able to more intensely study precipitation in ferrite, and we used that technique to discover interface precipitation in my research at US Steel, which I'll come to later. It was very fashionable for PhD graduates, particularly in metallurgy, to emigrate after they obtained their PhDs, and principally to the States. And at one point, I think it was estimated that 80 or 85% of all metallurgical graduates emigrated. This was a few years, it was called the brain drain, and there were no quotas at that time. It was very easy to get a visa with a PhD. Bill Morrison had chosen that track. He was already working at US Steel, and he wrote to me. We didn't have emails in those days, maybe telephone me, and he said, "You've got to be a fool not to come to the States and apply your knowledge." There was a very big interest in high-strength, low-alloy steels in the States and virtually no local expertise. So I was interviewed by various North American steelmaking companies, LTV, Bethlehem Steel, US Steel, by Dr. D'Orville Doty, a well-known welding engineer. I was interviewed in London. I was offered a job. I'd never been to the States, but I got on the Queen Elizabeth in Southampton and showed up in Monroeville in the Research Center for US Steel, which at that time was arguably the strongest steel research center in the world, with luminaries such as Ray Grange, Oriani, Bill Leslie, Al Kay, Bob Fisher, with the most well-equipped laboratories, microscopes, 3 or 4 microscopes in my group alone, compared with one at Sheffield University, which we were lucky if we could use that microscope for one hour a month. At US Steel, I stayed there for 4 or 4.5 years, and while we had the wonderful facilities to do excellent research and to publish papers, the work on interface precipitation. I'm a co-inventor of the interstitial free steel at US Steel with Peter Mould. There was a frustration that the US Steel didn't apply those ideas. So after 4 years, I left US Steel and I joined Molybdenum Corporation of America, which is known as Molycorp for short. And Molycorp at that time owned 49% of CBMM, which is the largest producer of niobium in the world. And this, ironically, was the first time I knew where niobium came from. My interest in niobium was not related to promoting niobium for a particular company. It was from the scientific point of view. And I established in my research that niobium, and niobium working with boron, niobium working with molybdenum or niobium molybdenum boron, the very strong synergistic effects on transformation. And we developed all kinds of steels, including X80 steel for the potential Alaskan oil pipeline, the Alyeska pipeline. But US Steel was not a successful bidder. That order went to the Japanese, Nippon Steel and Nippon Koken. And so this was very frustrating in that US Steel didn't have the commercializing ability that perhaps J&L did. Mike Kaczynski put out 3 or 4 products a year, new products. We couldn't put one out at US Steel, so on the basis of that, I left to join Molycorp. After 5 or 6 years at Molycorp, I had developed the niobium technical development program, which was run in conjunction with Molycorp's molybdenum development and rare earth development program. I'd enjoyed advanced management training in University of Western Ontario, and I had developed enough contacts and confidence that in 1976 I left Molycorp and I established my own company, Microalloying International. The first 2 clients for that company were Italceda. I'd have a relationship with Italceda as part of the market development program, and I had a direct relationship with my friends at CBMM, who asked me to establish a technical development program independent of the blended program which was being operated at that time by Molycorp. If we think back to the early years of that niobium technical development program, one could be considered courageous to join a little-known Brazilian company. But CBMM, particularly in comparison with Molycorp, was a very sophisticated company. The owner had been the former ambassador of the United States, he'd been the finance minister in Brazil, and he had a long-term plan for development of the niobium Araxá mine. A very long-term commitment to spend money on technology, on traveling, on teaching. And as a result of that philosophy, the year after I started the consulting with CBMM directly, we visited the former Soviet Union in 1977 and signed a long-term technical and cooperation agreement, which still exists today. And in 1979, we arrived in China, a long time before it was easy to get there, and using the facilities of the Brazilian consulate and the embassy, which Walter Moreira Salas had some strong control over, we were able to make the direct contacts with the Central Iron and Steel Research Institute in China and with the emerging steel companies there. So the long-term philosophy of CBMM and style and willingness to commit funds to disseminate the knowledge of niobium, that was a very big attraction there. As a result of that traveling, the luxury of traveling, I was able to meet all the specialists of the day. We had unlimited traveling budgets, which may sound strange, but we had unlimited traveling budgets. So I could get to know my friends in Japan, Isao Kazasu, Tomo Tanaka, Hisashi Gondo, Takechi, working on cold-rolled steels. And we opened an office in Tokyo in 1980, which I was personally responsible for supervising for the following 5 years. So the philosophy of CBMM and the close relationship was a very important vehicle for my being able to go out and promote or propagandize my ideas. And that is a very fundamental component of emerging today as a long-standing expert. It all came from being able to meet the experts worldwide and to travel and to present papers and go to as many technical conferences as I wanted to go to. I mentioned earlier that I was able to travel, so I was able to meet a lot of international experts in this field. But also, I'm known today as an expert in pipeline steels, but my history in pipelining started in the early 80s. Before that, I had a strong interest in weight saving in automobiles. Worked with Siggy Hecker when he was at Chrysler. He taught me about forming limit diagrams. Peter Mould taught me about texture development and through thickness resistance to thinning and plastic anisotropy. I had an interest in welding, for welding my early steels with low carbon and higher levels of niobium. And I discovered the seminal work of Philip Kirkwood. I traveled with him and introduced his ideas to Lucan Steel and McDermott and fabricators of steel. And while I was traveling, as an example, I learned about the metallurgical nuances of boron titanium wires, which Phil was the co-inventor of that with John Garland. So with time, I got interested in ductile fracture propagation. I got to know Ernie Shannon at British Gas and Jeff Fernioff, the Ibers and the Maxes who gave rise to the Battelle equations. And more recently, I've had the good fortune to be applying some of that knowledge with my colleagues at the Rosniti Research Institute in Chelyabinsk, with CSM in Rome. And the CSM work in Rome is being sponsored currently by China National Petroleum. So I've been able to use my broad reach, if you may say that, or broad interest in subjects. They're not peripheral, the fundamental aspects of microalloy steels. The end user is interested in all those subjects that I mentioned: toughness, formability, fracture arrest, and the like. In recent years, my contribution to the field of low-carbon microalloyed steel metallurgy, particularly niobium versions of those steels, has been recognized. And I've modeled my career on the work of Norman J. Petch, that Jack Woodhead was a big admirer of Norman J. Petch. for his consistency, whether he was working on the structure of cementite, working on toughness, yielding behavior, dislocation theory with Cottrell. He always shone in each of those fields of endeavor at the time. So I strive to be consistent, competent, and trustworthy in all my work. As far as my professional accomplishments are concerned and the areas why I'm proud, it's interesting to see one's ideas applied in practice, in engineering steels, in structures, and not in just presented in technical papers. The frustrating thing is it took 35 years for the 0.02% carbon, 0.1% niobium metallurgy, the steels I studied at Sheffield, to actually find a real commercial application. And it was through my project involvements with Pemex for the Cantarell project in 1998. We were able to apply the low-carbon niobium HTP concept in that Cantarell project. A few years later, we applied the same metallurgy for the Cheyenne Plains X80 pipeline, which at that time was the longest X80 pipeline in the world, 680 kilometers. Then a little later, through the long-term program in China, China National Petroleum had a curiosity to see how the Cheyenne Plains project was executed. And we received a large delegation from China. They came to Cheyenne Plains offices, they came to the right-of-way, we took to the CRC Evans, they talked to installation contractors, and more or less on the spot decided that they would adopt that Cantarell Cheyenne Plains metallurgy, which was basically the Sheffield metallurgy of 35 years ago, or 35 years before. So I was able to introduce that metallurgy more or less unobstructed because I advisor to the project manager. I was trusted by the project manager, trusted by the steel makers, trusted by the pipe mills, and the final end user, that we were able to put those steels, that technology in place after such a long delay. So, additionally, through my relation with Bard Hyemans of Enterprise Products, we applied the HTP metallurgy in the deepest pipeline in the world, in the Independence Hub, in 8,000 feet of water. We were only able to do this through the long-term, as we mentioned before, trusting relationships. And in that case, the role of my CBMM friendships became paramount, in that the steel for the Independence Hub, the plate was rolled in Azovstal by my friend Dr. Nozachenko. It was made into pipe in India by Braja Mishra and his colleagues. These are all contacts that I enjoyed through the CBMM technical development program. So the accomplishments took a lot of effort, took a lot of time, but it also took a whole matrix of friends and colleagues that I'd got to know over the 50 years of my career.
When I landed on these shores in the autumn of 1958, it was my intention to get into the iron and steel industry. In India, I had studied geology, but I thought iron and steel was more important to India at that juncture because we were a new country and very short of the commodity like steel. And so I came to these shores as Jamshed Irani. My real name is Jamshed. Jamshed is named after one of the old Persian kings. But as very often happens, the local boys in Sheffield cut down my name from Jamshed to Jim in a very short spell, and I was always known as Jim Irani. As far as my previous education in India was concerned, I had a good academic record, and ultimately I won the scholarship of the Tatas on that record and came here on a Tata scholarship for a period, supposedly for a period of 2 years. It was my original intention to stay in this country for 2 years, which was heightened by the advent of the winter, because as soon as I came, the winter months were on me, and I said, I'm not going to stay here for more than 2 years. Ultimately, I stayed for 10. So much for trying to decide on my future. I had a thoroughly interesting and a very rewarding time in Sheffield, enjoyed myself, stayed with the local boys at houses of residence and so on. In India, the education system is quite different. You actually study from home. In fact, for the first 22 years of my life, even at university, when I joined university, I used to live at home with my parents. And that, of course, all broke down when I came to these shores. But I think I adapted fairly easily, and my earlier training in geology, I could see was not going to get me very far. So I moved over to metallurgy, and I took the 2-year course at Sheffield, and it was tough going. One thing about British weather is that in the winter months it's cold and dark and not very conducive to going out. So you stay in your rooms, and it's very helpful in a way to keep you in the room and studying more and more. Another interesting feature which I remember was that in 1958, television had not yet come to India. So when I came here, I saw television for the first time in my life at the age of 22. And I would watch BBC programs almost endlessly. Whatever was on the box, I would watch. But after 6 months, I got, shall we say, tuned to the fact that I only have to watch what I'm interested in and not as a curiosity. As far as metallurgy went, even if I'm immodest, I think I can say that I did rather well. And Professor Honeycomb, who was the one who induced me and helped me to get into Sheffield and to study metallurgy, in his group of boys, I always stood out first in the written exams or whatever else we had to take. And I got my master's degree in metallurgy in 1960. Actually, that was my original aim when I came from India. But then Professor Honeycomb mentioned that, look, we could, your Indian scholarship might be over, but we could give you a scholarship in Sheffield also to study for a PhD. He was interested in the properties of microstructure, relations between microstructure and physical properties of steel. So Jim, why don't you stay over and I'll find you a scholarship? So I said, fine, if you can find me a scholarship. And I got a scholarship from one of the steel companies, also with a written statement saying this is what I should be studying for them. I spent about a month looking at that and wrote out a research program, took it to Professor Honeycomb, and he didn't even look at that program. He said, are you sure you've got the money from the steel company? I said, yes, here's the letter saying that they will support me for 3 years. He said, that's good. Now you forget about what they want you to do. I will tell what I want you to do. And that was how our relationship, which was very warm. Professor Honeycomb came out to India after I came back, and I toured the country, took him around India to several places. So we had a very warm relationship, Professor Honeycomb and myself. I stayed there for 5 years in the halls of residence and thoroughly enjoyed myself. And my friends from some were from metallurgy, others were from different departments. Come spring and summer, we started playing cricket. I was, by the way, a reasonable cricketer even when I was in India. I played for my home university in India. So when cricket started around April, I came to these shores, as I said earlier, in September, October. When cricket started in April, I felt very much at home and played for Sheffield University. You know, Professor Honeycomb was a pioneer in trying to understand the relationship between microstructure and mechanical properties. And in Sheffield, we had an old, what was known as EM3, a very poor quality electron microscope, but the thing at that time. And by the time I finished my master's degree and enrolled for the PhD degree, Sheffield University was the proud owner of the latest electron microscope at that time, EM6. So myself and one or two others, there was one person I remember from South Africa, Vanus Wagen, and another one was a local boy. Three of us formed a team to start looking at these microstructures under the electron microscope. First using carbon replica techniques, which were the best then, but nothing compared to what is available now. And of course, once the EM6 was installed, we developed the technology for making thin films and adapted ourselves to transmission electron microscopy. And that was, in my opinion, a real breakthrough for understanding the properties of steels. And my later work in Bisra and other places, who also had good electron microscopes, was based on that. And I would have continued with electron microscopy even after going back to India, but for the fact that there was no interest in India at that time in electron microscopy. So I had reached a peak in Sheffield, and I didn't want to go downhill in India, so I had to give up electron microscopy. But for about 5-6 years, including my PhD degree, I was a born electron microscopist, very interested in that. You know, after I got my PhD, and immodestly I can say that I was awarded the gold medal at that stage for my PhD work under Professor Honeycomb. Then I had to start thinking of what next. And even at that stage, I had already spent 5 years in this country, but I thought that maybe some industrial experience will benefit me. And Bisra, the British Iron and Steel Research Association, with whom I had already made contact during my PhD work, was just downhill from St. George's, where I studied I worked for my PhD. And there was a gentleman there, unfortunately, he passed away only last year, Mr. Eric Duckworth. He operated from London, but his laboratories were in Sheffield. And I joined those laboratories. He was interested in a way, continuing the work of Professor Honeycomb, correlating microstructure with mechanical properties. And he offered me a position in the physical metallurgy division, which I took up. And within a year, my boss, who was the head of the physical metallurgy division, Rodney Phillips, left Bisra, and I was offered that position to head the physical metallurgy division. And I was very grateful for it, and I continued in that position for another 3-4 years, till ultimately I went back to India. But those 3-4 years were very, shall we say, rewarding, because that was, as I said, mentioned before, it was just a time when people started looking at microstructures and correlating them with physical properties. I would liken it to the earlier stage, where in fact I would say that it was like, trying to find out, as far as steel is concerned, everyone would know that steel is endowed with a lot of variations, crystalline structure, transformations, and so on. So it is a rather complicated system to understand and correlate microstructure with physical properties. And before the electron microscope and transmission electron microscopy came in, it was like it was like trying to find out what's wrong with the engine in a motor car without opening the bonnet, because you couldn't look inside. So without opening the bonnet, whatever sounds came out of it, you would try to say that, well, there's something wrong, but you couldn't actually see what's wrong. Electron microscopy broke that barrier. We could now open the bonnet and see what's wrong with the engine. And transmission electron microscopy was the key factor. And after that, of course, there were many schools. There was one very good school not far from Bisra, which was headed by Jack Irwin and Brian Pickering and some other colleagues. Terry Gladman was at Sheffield University. All these people were, Bill Morrison, all these people were pioneers in trying to understand what happens to steel when it goes through various physical changes, morphologically and so on. And it was a very interesting period to correlate what we were then seeing under the electron microscope with the properties which were mechanical, which people knew, in fact, for many years. And I think the ultimate success was that what had been projected by people who did not have electron microscopy but would know what physical changes have taken place and would surmise and in theory say that, look, this must have happened for the particular property of a steel. When we started looking at it under the electron microscope, those people were proved right. So in a way, it was something which we knew existed, but we couldn't see. As I said earlier, it was like opening the bonnet of the car and saying that, yes, the engine is missing or the engine is sputtering because of this reason, and it was so. So it was Bisra's role to develop newer and newer steels and make them applicable for tougher and tougher environments. And I think the most valuable tool was the electron microscope, because that enabled us to see what was happening, precipitation, how the dislocations were moving inside the material and so on. And it was Bisra's stated aim to develop newer, stronger, and tougher steels. And that's the program I got involved in once I took over as the head of the Physical Metallurgy Division. There was a conference in Scarborough in 1967 when I think for the first time Bisra presented its results. I was the head of the thing. I had the honor of being the head of a team, but there were excellent people like David Burton, Derek Jones, Brian Rothwell, Jeff Tither, who were in my team, and it was an honor and an experience to work with them. And each one had his own contribution. Some of them were mechanical engineers, so they were very interested in developing equations and theories about correlating the properties to the treatments which we were subjecting the steels to. And I think that 1967 conference at Scarborough was the key point. I left almost immediately after that 1967 conference, but that was the key point in which Bisra's work was highlighted. So that's the type of work which I did, and I thoroughly enjoyed it for 5 years in Bisra. When I went back to India, it was my intention to continue with that work, because by that time electron microscopes had come to India also. But it was unfortunate that I was not given the necessary encouragement to do that electron microscopy. And a little known fact I could now divulge, and that is that when I went to India, BISRA were good enough to give me a lien on my job for a period of 1 year. Eric Duckworth said that you can come back to this job or even a better one, but since you want to go back to India, go now and look for yourself. I went back, I looked for myself. J.R.D. Tata, who was in charge of Tatas then, gave me a good job, but after 8 or 9 months, I told him that, look, research and development in India is far behind what I could do in Sheffield. So excuse me, I would like to go back to Sheffield. In fact, I had put in my resignation. And J.R.D. Tata said, hey, hold on, we'll offer you another job. Because that 1 year period was not over. And the lien was not over. So I took up that other challenge, and that was to work in a steel plant. And far, far away from electron microscopy, I might add. I even had to do some shoveling of fluxes and ores into open heart furnaces and things like that. But I enjoyed it. And that's where my career finally was built up, in the steel plant rather than in the laboratory. So I broke the link with BISRA and continued in India. As far as the work on controlled rolling is concerned, it soon became apparent. Of course, it was known for years, even before the scientific studies were that if you handle certain steels, whether it was their cooling rates or the temperatures from which they were cooled, you could get excellent properties, far better than the normal mild steel properties. And but the bottleneck was the equipment. I found that out also when I went back to India, because I wanted to do some controlled rolling as a junior officer to start with. And the plate mill person who was there, in India, absolutely refused to lower the temperature. He didn't want to break his mill, as he said. So it was a lack of facilities which in fact held back the development of controlled roll steels. But the data that we produced, both in Sheffield, some of it in India, very little in India, and of course on the other side of the Atlantic, there were plants like Burns Harbor, which were coming up, which were using these new methods of controlling the properties of steel through manipulating the rolling technologies. Temperature of quench, rate of quench, to what level, chemical composition, of course. And the chemical composition that we were playing around with always was aimed at lowering the carbon equivalent to as low a point as possible, because the lower it was, the easier it was the material could be welded. No point in producing an excellent piece of plate or rod which could not be joined. So these were the developments taking place, and I'm delighted that in Jamshedpur also, I started this control rolling in Jamshedpur in the early 70s. But it was not till the early 90s, 20 years later, that we finally have an excellent hot strip mill supplied by a German company, and where there is laminar flow, cooling and so on, where the steel coming out can be quenched. It also is what we call a roller quench process, where the steel is, as it comes out of the roughing mill, it is rolled, and then after holding it for some time, it is again pushed through the finishing train. As a result of that, we can have a whole range of properties from basically very few steel compositions. Otherwise, earlier, to have the slightest change, we had to change the composition. Now we don't have to change the composition so frequently. The same properties can be achieved in similar compositions by controlling the rolling techniques, temperature to which it is cooled down and then quenched, tempered, and so on. There's a whole host of treatments that can be done, so that from basically the same steel of good weldable quality, you can get a range of properties depending on what you want, whether you want higher strength or you want higher, not so higher strength, but coupled with toughness and so on. So that's how the controlled rolling came in. You know, steel is such an interesting material and a wonderful thing for the research people to play around with, if that's the right terminology. I remember at Sheffield, I discussed with Professor Honeycomb certain properties we wanted, and we went through the periodic table of how to get those properties, and we found out that the best element which would respond to what we wanted to study was gold. And because gold doesn't form a carbide, it doesn't form an oxide, it has an atomic size which is significantly different from the iron matrix. So those physical properties could be studied in tinfoils by adding gold. Of course, nobody would, in his senses, would commercially think that was the solution, but we put it in just for theoretical studies. So similarly, the search was on, and I would say that this was in the decade of the 60s, that what could be a material which could transform steel from a ordinary mild steel type of things to a more specialized material. And studies showed that the appropriate material and very small amounts of it would be niobium. And I think it was at that time in America called columbium. And the studies were carried out on both sides of the Atlantic on how to take maximum advantage of it. The great thing about niobium was that it didn't form an oxide, obviously, but the carbide also was susceptible to changes at different reheating temperatures. And the solid solubility of niobium in iron was limited. So it would be easy to form precipitates. And the type of precipitate, whether it was too fine or coarse, would depend on various reheating schedules. So very small quantities of niobium could have a great impact on the properties of steel and have an effect on the way it recrystallized into austenite. It could have an effect on how quickly it could be taken back into solution depending on the temperature that you heat the material to. It was a very flexible and a very, shall we say, obvious material to use for steel to get a range of properties. And people used to put that in and really play around, you know, the quenching temperature, the quenching rates, and recrystallization and so on. And once again, though some work was done even before the electron microscope came, it really took off with electron microscopy, because then electron microscopy could show you the evidence that the steel is behaving in a particular manner because the niobium carbide usually is behaving in a certain manner. So it was very easy to correlate the heat treatments and the properties of mechanical properties of steel with different levels of niobium. I think niobium in a way saved the day for extending the innings of steel. If it had not been for that, then maybe there were other elements like titanium, vanadium, but they could not replace niobium. Niobium was definitely a stellar performer as far as treatment of steels was concerned. To make carbon, it is easier to put in 0.1. Economically, of course, it is expensive, but economics also, shall we say, is justified by putting in more niobium, because the steel becomes far more pliable. I don't mean physically, but chemically. You can do a lot with a steel with niobium in a way to govern its properties, govern the property of the given piece, rather in material which is having niobium as compared to something which doesn't have niobium but has only manganese and carbon. I'm not very sure whether I'm putting it in the right manner, but it's like having a good lubricant in a car which extends the run of the vehicle rather than by, and it's run of the vehicle, and also, shall we say, controls properties over a wide range. You don't have to be too specific. You can always get very good properties in a piece of steel if you are very particular about the temperature and you heat it to and how much deformation you give it and so on. But practically, it is not a solution, because you cannot, shall we say, aim for a spike in the heat treatment. You need something which has a plateau. So even if you are a bit off, and in industrial, shall we say, experience, industrial rolling, you can't say that I'll want that temperature, 955, that will give me very good properties. You're likely to finish with 930 or 985. And even if you finish with those, you still require the properties that you want. And niobium helps to, shall we say, flatten the spikes into plateaus. So you get good properties even with varying physical treatment conditions. It was only fate, I think, and circumstances which drew me away from the laboratory into the steel plant. But then as things turned out in the decade of the 70s and 80s, decades of those days, I rose in the steel plant. I don't know whether it was luck or effort or whatever, and ultimately finished up running the largest steel plant in India. And even now, there was one thing wrong with that plant: it was not modern. I remember telling Mr. J.R.D. Tata one day, who I look upon as my technical godfather, so to speak, that unless we modernize this plant, this was in the 80s, both you and I would be standing at the gate of the steel plant in Jamshedpur selling tickets, saying, please come and visit the steel museum, because we were becoming a museum. So he laughed a lot, but then from then on we started modernizing, and throughout the 90s we modernized it, and at the beginning of the century we were the most efficient, lowest cost modern steel plant in the world, beating even the South Koreans. So that was Tata Steel in Jamshedpur. Steel is such a wonderful material with physical changes and properties which are dependent upon those physical changes, that one can spend a lifetime, several lifetimes, trying to decipher how to get it better and better.
Well, my schooling was pretty conventional for the time and place. We're talking about 1950s England. I grew up in Nottingham, and I ended up going to Nottingham High School. It was a place that had a pretty good reputation around the district, and I was lucky enough to get a scholarship to go there. Between school and going to university, I took a year off. It wasn't really a year off, it was a year working, and I worked in the metallurgical labs of a local company. Not much ferrous metallurgy, but certainly some exposure to laboratory techniques, metallography, mechanical testing, and so on. I went to Imperial College, the Royal School of Mines, to study metallurgy. In my last year at Imperial College, as I suppose is normal, we had several interviews to see where we might be able to find a job that we thought was interesting and so on. I had one interview at the London headquarters of BISRA. BISRA had a number of laboratories in different parts of the country, but the headquarters was here in London. So I showed up for this interview, and one of the things that I was asked while I was there was, what do you know about the Petch equations? Well, that was a lucky one because I did know something about the Petch equations, so I expounded what bit I knew. And I was told that, well, there might be some people in Sheffield who'd be interested in talking to me. And they were working on hot rolling. So I thought, well, not sure how that's going to fit because I'm going to finish up as a physical metallurgist, and that sounds like a mechanical metallurgy kind of thing to me. But anyway, I went up to Sheffield for an interview with Rodney Phillips and John Chapman, who were doing the early work on controlled rolling of low-carbon microalloyed steels. And then I understood, because really it was all about understanding the physical metallurgy of those alloys. I was fortunate enough to be offered the job, and for one reason or another, I thought that was the best of the opportunities that I had, and so off I went to Sheffield to work with John and Rodney. I started to work on the physical metallurgy of austenite processing in microalloyed steels, and became convinced fairly early on that it was a very, I'm not going to say complicated, but a lot of interactions between precipitation processes, deformation processes, recrystallization processes, and those were the things that basically determined the austenite structure that you would finish up with, and hence the ferrite structure that you would finish up with after transformation. So in order to understand how to use controlled rolling properly, what we now call thermomechanical treatment, you had to understand what was going on in the austenite and how it was influenced by all of these different processes. So when this initial work was done, we presented a paper at a small conference in Sheffield in 1966, summarizing what our ideas were up to that point. And later on in 1967, some of these same ideas were presented in a couple of papers at the Scarborough Strong Tough Structural Steels Conference. Unfortunately, in some ways, the original paper that we presented in '66 wasn't published until after the Scarborough Conference, so there's a little bit of a confusion about where some of the work comes from and who did what to whom, but it's all there in some form. Unfortunately, for a number of reasons, I didn't get the whole story written up until quite a lot later. It was actually published in French in 1972, and therefore hasn't been very widely understood or recognized. So that's one of those things that sometimes we get sidetracked by life and other things and don't get the stuff written up as promptly as we should do. Anyway, in the end, it was all done. So overall, at that time, the BISRA labs in Sheffield were a great place for a young metallurgist to work. There were lots of interesting things going on outside the lab. Among other things, we had sports teams. We had a rugby team, and we had a cricket team. I remember playing with Harry Stewart, Jeff Tither, and of course Jim Irani on that cricket team. It was interesting. Jim certainly was in a different class from most of the rest of us. He'd played for the university, he played in the Yorkshire Leagues, and we were playing at the lower level of the Sheffield Industrial League, so he was usually a pretty effective bowler mainly. Every now and then somebody would get after him, but not usually. He had a pretty good record at that level. The start of the whole thing really was a world tour that was undertaken by the division head the previous year. That would be in calendar 96. One of the places that he visited was Australian Iron and Steel in Port Kembla, New South Wales, and he was impressed with the people there and with some of their thinking. So he had the thought of arranging an exchange between young metallurgists. So off I went to Australia, and Terry George moved to Sheffield to work in my place. I really think I got the better of that deal, but certainly Terry did some very good work on titanium nitride while he was at Bisra. So when I got to Port Kembla, it was quite a different environment to work in. I was now working day to day in a major steelworks. As luck would have it, an inquiry came in while I was there from the Victoria Pipeline Commission. They were looking for steel to make pipe for the sale to Dandenong Pipeline, which I think was the earliest major onshore gas pipeline in Australia. There was really no local experience in this kind of material at the time. The steel was made as fully killed steel. It was cast into 20-ton ingots. There was no ladle deoxidation, and all of these things together make it quite difficult to get good transverse toughness properties. We did lots of different things. We tried casting smaller ingots, tried rolling the slabs 100% in the transverse direction. We made, I think, the first rare earth treated steels in Australia. Somehow or other, with one or other of these options, we succeeded in getting the properties that the Victoria Pipeline Commission were looking for, but it certainly wasn't an easy thing to do at that time. I think the metallurgical challenges of producing some of the stuff that was needed at that time. There were some significant changes going on in terms of the materials that were needed, and it was a learning process for all of us, including the most experienced of the people in the plant. We were basically doing our experimentation using 300-ton open hearth furnaces, so it is a far cry from trying to do the same sort of thing with 50-kilogram vacuum melted heats at Bisra. That was quite a step up in scale. As a supplement to that year in Australia, I also spent a few weeks in India on the way there, and saw quite a few interesting things, as you might suppose. I was in the Tata steel plant at a time long before the changes that Jamshed Irani was so instrumental in promoting had taken place. It was quite a different environment. Much more small scale and manual, I guess you would call it. And I also carried out what I think were the first controlled rolling trials in India in the Hindustan Steel plant in Rourkela. The move to Italy was relatively serendipitous. The CSM celebrates its 50th anniversary this year, but at the start it had no laboratory facilities. The impressive facilities about 25 kilometers south of Rome were being planned and built. In the meantime, however, they started recruiting professional staff, and they placed them at various different research laboratories pretty much throughout Europe. It happened that there were 3 such people sent to the Sheffield area, 1 to Swindon Labs in Rotherham, and 2 to Bisra. I was actually away in Australia at the time these people showed up. However, when I got back, I became good friends with them, and that is really where the relationship started. And so I called Valerio Facenda, who was one of the people who'd worked at BISRA, whom I got to know quite well, to see if there was any possibility of my going and working in Rome. As it happened, there was a group under Piero Brozzo that were interested in microalloyed steels, in weldable steels in general, and it seemed like there was going to be a fit there. There was a group working on welding, weldability, weldable steels, and so on, under Franco Bonomo, who became my colleague and nominal boss. Franco had a background in welding. He'd spent some time at BWRI, which the forerunner of TWI, of course, which at that time was one of the top welding laboratories anywhere in the West and perhaps anywhere in the world. I had all the equipment that I needed there for making real welds, simulating welds, testing real welds, testing simulated welds, and that was where I started to work on the heat-affected zone properties of microalloyed steels. In terms of the metallurgy of austenite processing, I think it's probably fair to say that at BISRA we had been a little bit ahead of where the CSM had got to at that stage, and I was able to continue my work in that area with some profit while I was at the CSM. There was a significantly bigger three-high rolling mill, which was more suited to simulating the industrial plate rolling process than the 10-inch plate mill at BISRA. There was also a significantly larger air melting furnace, and that was kind of useful. We'd found out in Australia how important the influence of residuals could be, so working on air melts rather than vacuum melts at this stage was probably a useful step forward. Among all of the microalloying elements, as far as austenite processing is concerned, I think it's fair to say that niobium is the most important one, because it's the one that you use above all to control the developing microstructure of the austenite as you do the thermomechanical treatment. It was the basis of the controlled raw materials, and I think that if you look at the sequence of the publications in the 1960s, it likely is fair to say that nobody was quite sure why it was the one that was absolutely needed in controlled rolled steels. That kind of came out over the work that was done in the 60s, say between maybe 1964 and 1969, something of that sort. That was the period in which I think it's fair to say the essential characteristics of niobium and the precipitation of its carbonitride were fully appreciated. As far as the move to Canada to work at the Noranda Research Centre in Montreal, basically I was headhunted while I was in Rome. I had really a lot of freedom in terms of what I did and how I did it. My boss, a guy called Jean Fage, was very easy to get along with, easy to work with, and there was general direction in terms of the sorts of things that we needed to do, but otherwise it was pretty much up to me. So I carried on doing a fair amount of work in the area of particularly heat-affected zone toughness of HSLE steel weldments. I had the full kind of range of techniques again to use, both simulation and real welds, although in this case both the simulation and the real welds had to be done elsewhere. There were no in-house facilities for that. I also did some work on direct quenching and tempering while I was there. Jeff Tither had done all the groundwork for that particular process at BISRA, and I wanted to continue that and see if there were ways of trying to make the process a little less sensitive to how you did the quenching. Jeff actually, while he was still at BISRA, had dreamed up the idea of interrupted quenching, where rather than quenching all the way out to ambient temperature, you would interrupt the quenching partway through and allow the subsequent air cooling to control the properties rather than coming back and tempering. One of the major issues that I was looking at was the effect of niobium and other microalloying elements on heat-affected zone toughness in weldments in materials having different levels of hardenability. The hardenability elements like molybdenum, like nickel, like manganese, because these, for a given level of cooling rate, will react in different ways to the effect of the microalloying elements that are present. I made contact with John Jonas, who had been in Sheffield at the university when I was in Sheffield, and got to know his research group, the Lutons, Isaac Weiss, and several other characters who were working on recovery and recrystallization. There were other people involved in the welding-related projects. Brian Gravel was at Dominion Bridge at the time, and he was responsible for making a lot of welds in the project that I was carrying out there. That was before he moved to the Welding Institute of Canada to do a lot of the metallurgical work that he carried out there. By 1979, it was pretty much impossible for anybody with a strong interest in pipelines to stay away from Calgary, because that's where all the action was, and there was a lot of action at that time in that general area. I initially joined Foothills Pipelines, which was a company that had been set up to build the Canadian portion of the Alaska Highway pipeline system, which was planned to bring gas from the North Slope of Alaska down through Alaska, through northern British Columbia, through the Yukon, through Alberta, and eventually out to ship gas to the US Midwest. It was quite an ambitious project. Very shortly after getting to Calgary, I got heavily involved in a program of full-scale gas pressurized burst tests. We had a lot of help in the early days from people from British Gas, who already had quite a few of these kinds of tests under their belts. And we were able to move ahead on, as it happened, a very tight schedule to get a significant number of tests done. When we carried out these tests on the very tightest of timelines, got all the results that we felt we needed to plan the fracture control design of the pipelines we were going to build, it became clear that the actual project was not going to go ahead anytime soon, and that has been a bit of a history over some decades now. What was going to happen was that we were going to build the so-called pre-built portion of the pipeline system through Alberta, southern British Columbia, and into Saskatchewan. And in building this part of the system, we were able to work on some advancements in the pipeline technology at the time. The whole thing, almost the whole thing, was built using X70 material. A lot of it was built using mechanized gas metal arc welding, and most of it was coated with fusion bond epoxy coating. So we did actually move ahead significantly through this project. By that time, I'd moved to one of the parent companies, which was Alberta Gas Trunkline. There I was extremely lucky with my boss, who was Eric Shelton. Under Eric, there were 3 departments that looked after quality management, materials, and welding technology, and I had the small group that did the welding technology. Later, Eric became the first non-American chairman of the Pipeline Research Committee, which I think was a major step forward for that organization. So under Eric's leadership, we built up some significant laboratory facilities that enabled us to do a lot of things in-house that most companies were not able to do. We did a good deal of work on weldability of the new pipeline steels that we were using. We established the usefulness of the Urioka carbon equivalent formula for determining cold cracking susceptibility of pipeline steels. That's currently in the Canadian standards for pipeline steels and for pipeline systems. And I think it's a convenience in that we don't have to hop about between two different carbon equivalents as you do when you're using API steels. So as part of our plan to try to make new pipelines more efficient and more economical, we carried on trying to move the strength levels further and further forward. And the first thing we did back in the early 90s was to move into experimental X80 grades. These, again, were microalloyed steels, always niobium, sometimes molybdenum, sometimes vanadium, sometimes a cocktail of just about everything to make everything work together. The critical part of producing these higher strength steels, of course, was the widespread availability of online accelerated cooling, which allowed you to control the transformation microstructure much better and to move the strength up without compromising the fracture resistance. We've done quite a bit of work on X100 as well in conjunction with a number of different pipe producers in different parts of the world. There's a fair amount, I suppose, kilometre by kilometre, actually has been installed on the Transcanada system, but it always seems to be that when it gets to a really significant project, the people who make the decisions about these kinds of things figure that it's just a little bit too much of a risk. Nobody is really comfortable with going ahead with it. I think we felt as technical people that we dealt with all the issues, we got the right welding consumables, we knew how to weld the stuff, we knew what sorts of toughness levels we needed, and the technical package is there, but I think it's just slowly moving the comfort level further along so that we can actually benefit from those significant increases in strength and therefore significant reductions in tonnage of steel. It was Eric Shelton who got me involved in the Pipeline Research Committee, as it was at the time, became PRCI, in the NG18 committee, as it was, later became the Line Pipe Subcommittee, the Structural Integrity Subcommittee, and a whole bunch of other things. After I'd been with that committee for a little while and got myself adapted to the way it worked and so on, I got quite heavily involved in some of the projects, including one that I recall in the middle 80s with Malcolm Gray on different ways of looking at the ductile fracture propagation problem. We never quite got that to a practical conclusion on that first go-around, but it seems now that some of the ideas that came out of that project are quite relevant today when we're beginning to realize that in the very tough materials that we're dealing with now, we're probably not really looking at a traditional fracture problem at all. It's more a question of propagating collapse and some of these issues around the tensile properties of the materials, how they succeed in distributing strain under biaxial tension conditions are more relevant, and they will work better than traditional fracture-based approaches. Eric also is to blame for getting me heavily involved in the Canadian Standards Association work on standards for pipelines and for pipeline materials. I'd done a fair amount of work with different subcommittees prior to this time. I stayed involved with the PRCI work pretty much through the end of my career with Transcanada Pipelines, and even from time to time since I retired from Transcanada. Last year, for example, I was lucky enough to go to the 19th, I think it was, joint technical meeting between PRCI, the European Pipeline Research Group, and the Australian Pipeline Industry Association in Sydney, and that was a really good opportunity to catch up with a lot of friends that I hadn't seen for a few years. When I retired from TransCanada right at the end of 2007, I set up a consulting company, and I've been doing consulting work for TransCanada and a number of other companies essentially since that time. Probably the biggest project that I've been involved with was the Alaska Pipeline Project, which was a return of the scheme to bring North Slope gas down through Alaska, through the Yukon, northern BC, and down through Alberta, and connect up with the lower 48, much like the project that we've been working on in the 70s and the early 80s. This was a partnership between TransCanada Pipelines and primarily ExxonMobil. I worked for the most part on the fracture control design of this system. It was a high pressure system, 17.24 megapascals, I think, to be exact. It translates to a round number in pounds per square inch, I'm sure. And so the fracture control design was relatively exacting. We had, some issues that we had to deal with, which perhaps had not been faced before in X80 materials. Other than the work that I've been doing with TransCanada, I've worked with several other pipeline companies, generally speaking also on fracture control and sometimes on risk and hazard aspects. Since 2007, I've actually learned quite a lot about carbon dioxide pipelines. This required me to learn a lot more than I knew at the time about the thermodynamics of impure carbon dioxide. I was lucky enough on that to work with Kamal Botros at Nova Research and Technology Center. He did a very good job of essentially teaching me, or at least leading me along many of those aspects. Of course, in order to do fracture control design for a CO2 pipeline, you have to understand the thermodynamics of the specific CO2 mixture and how that links into the to the fluid dynamics and the gas decompression, or the decompression behavior of the fluid that's contained in the pipeline. It's somewhat more complicated than it typically is with natural gas pipelines. Between us, we learned quite a lot about this, and with Mo Mohitpur, who sadly died not too long ago, and two other colleagues, we actually put a book together on pipelining impure carbon dioxide for the ASME Press. And I'd be the first to say that the quality of the book as a whole is somewhat uneven, but I think there are parts of it that are excellent, and I think there's a lot of useful material in there that really isn't gathered anywhere else all in the same place. At the moment, there's quite a lot of interest in export of LNG from the west coast of Canada, and there are several large high-pressure pipeline projects in play intended to move the gas from generally the northeast corner of British Columbia over the mountains, which are pretty rugged between that part of British Columbia and the coast, take it into one of probably two coastal sites where there will be liquefaction plants and of course tank facilities. I've been involved, I am currently involved in a couple of those projects, again generally in terms of looking after fracture control issues, a few other issues, again related potentially with the safety aspects. I don't really have any specific plans to hang up my boots anytime soon. What I really need to do is to try to organize my time better. At present, I find myself, when I'm in working mode, I'm working just about every day. I'm not working full days, but every day is or every weekday at least, is a work day, and I need to get a lot better at organizing my time so that I can get a good run of free days and devote it to doing things other than work-related things while there's still time.